here we have 6-dimensional vector. And we divide the dimensions into 3 segments. Here. So each segment is only 2-dimensional vector. And then is the first, second, and the third. For the third segment, okay, we will use this cohort. Okay, we already built the cohort, so we can use like chemists to build the cohort first. So here you see with the cohort for the first segment, we have 256 centroids here. So here we just copy the code of each cohort is a vector here. Okay, so for the first segment, we just check which centroid is closest to this 2-dimensional vector. So here, suppose the second cohort is closest to this vector. So we can encode it is cohort ID to be 2, corresponding to the result. And for the second segment, we do the same things, apply the same process. Okay, so here we say it's a 123 cohort is close to a 2-dimensional vector. And then for the third, okay, it's close centroid. The ID is 87. So after it, we apply the quantization. The original vector now is quantized. We just keep the cohort ID here. Okay, so what we do? So with this representation, and we can achieve a very simple and memory efficient, and also we can compute the distance by using the asymmetric distance. So we say, okay, it's memory efficient. We can calculate it for you. So in the original vector, so if we use dou is 1. Okay, this is only 6 dimensions, but in our application, the dimension is usually very high. So suppose the dimension is 128. Okay. So each dimension you use 32 bits, 4 bytes. Use 4 bytes to keep in this vector. So in total, you need actually it's okay. You need 4,000 bits to keep the vector like this. But if we use the PQ, in PQ we only keep the centroid ID here. So if we use PQ, and suppose we segment it into 8 segments, and then each segment is represented by this cohort ID. Okay, so if we only have 256 code, then you just use 8 bit is sufficient. Right? 8 bit can be used to represent 256 different centroids. Right? So if your cohorts, the number of cohorts is 256, only 8 bits is sufficient. So we have 8 segments. So in total, we just use 64 bits to represent the quantized vector. The quantized vector like this. So how much will you use? You can see, compare with this. You can reduce 64 times. Okay, any problems? So it can save your memory life. And also, another question is, can we calculate distance between the query and this quantized cohort ID? Okay, no problem. We can apply a symmetric distance computation to do it. Okay, let me show you the process. Okay, so first, give a same block of memory space. Okay. So all the vector from S1 to Sn stored in your database, we apply the PQ, only keep their cohort ID to represent it. Okay, then it's called asymmetric because your query is the original vector, but your database vector is quantized. Okay, so it's in the, you can think they are in a different space, but we can reconstruct it. Remember? We can reconstruct this cohort ID by using this centroid vector. Okay, so all the ID you got just check. Okay, so for the first segment is the cohort ID is 42. You just check this cohort, and you can recover. Use this central to recover it into a two-dimensional space, two-dimensional vector. And for the second, we can repeat to recover it. And for the third, then we can recover it just by using the central vector to reconstruct it into come back to the original vector, the six-dimensional vector. Then we can compute with your query. And this is a method called asymmetric distance. Use the original vector Q and compute with the distance with the quantized vector X. Okay, you just use reconstruction so that we can compute this between them. And then we all the data, all the data, quantized vector, quantized data we have to reconstruct. So you have to do the reconstruction at times, and each time you have to compute the distance between them. It's still very time consuming. There's a trick to speed up. It's called a lookup trick. The lookup trick is we can create a distance lookup table for the given query. How to do it? So the idea is this. So you have first we create a table. It's a matrix like you have here we have 256. Each node we have 256 centroids, right? And each column we have 3 segments. Okay, so first we consider the first row. The first row is considering about your first segment. Okay, so we have 256 centroid. In each centroid, we can compute the distance with the first segment of query Q. Okay, so let's we can calculate the distance between the distance between the first centroid and the second centroid until to the 256 centroid with the first segment of Q. And the distance the distance is just a number, right? The real value the number. Okay, so we just store here for each centroid. Okay, then after this we can continue for the second row, means the second segment. For the second segment we can repeat the same process. Okay, we take the second segment here. The second segment is also a two-dimensional vector, and we can compute with the second segment's cohort each one. We just check the central vector, and also finally we store a real value, the value in each slot. It represents the distance between the centroid and the two-dimensional vector of the query Q. Here. And also do the same thing for the third segment here. You just repeat this calculation. After we fill up all the lookup table, okay, and this table, and then we can start to check all the database vector. And for example, for the first database, for x1, we can check its first segment is 42. Okay, so we just check the distance lookup table to check the first row, and is 42 centroids. Okay, and remember we store the distance here, right? Distance to the query here, so we already know its distance to the query. So we just keep the distance here, and for the second segment, we also check again, look up the table to see the second row, and for the 67th centroid to see what is the value stored here, and for the third segment, is ID is 92, so we check the third row and find the 92 centroid. And we just sum up all the distance is stored in that location. So we don't need to compute the Euclidean distance again. We just need to check the distance lookup table to see where they located, and just retrieve the value and sum up all of them. Then we can get the distance of x1 to the cube. Okay, any problems? 你们这样可以理解吗 Okay, alright. Okay, so by using this, you don't need to calculate the Euclidean distance with each data. You just need to find the ID and to look up table and then just sum up. So with this step, because you already compute all the distance with the query and the centroid. So when you get the centroid number, you just check out the table to retrieve the distance. It's only just one value, and retrieve the distance for the 42, retrieve the distance for the 67, and for the 92, and just sum up them together. It's much faster. Okay? So this is what we call a lookup tree. To compute the distance table here, and then you just check the ID to find the table to retrieve the distance back. It's very efficient. Then when you get the distance for all the data, you then sorting to see, do the sorting and retrieve the top K result to a user. Okay, any problems? Yeah, we already showed this figure before. Okay, so this is called a symmetric case. In symmetric case, the y and the x, okay, y is the database vector, and we will quantize. And for the x is your query. And the query is also quantized. So you will compute the distance between the quantized vector of x and the y. So the distance, the real distance is here, but after the quantization, the distance is back here. And this is a symmetric case. It's the original case, original distance between x and the y. But here, if we apply a symmetric case, the y is quantized to its centroid, but x is not quantized. We keep its original vector, so the distance becomes here. Okay, so we think with a symmetric case, it should be more accurate because your x, your query is not quantized. So your quantization loss, we don't need to count the quantization loss for your query for x. Okay, so intuitively it should be more accurate. Okay, later I will show the authors, they show just show some experiment for you, so to indicate that the symmetric case is indeed more accurate than the star by D. Okay, because you have a K star centroid, and the total length, the total size is, the dimension is D. So the total computation time is K star by D. But for ADC, you don't need to encode, right? For a symmetry, X is key for its original vector. So you don't need to do encode. You don't need to do compilation. Okay, so here is 0. But then compute. Next, if we want to compute the distance between the X segment and its central, the SDC, we don't need to compute. Yeah, because you already built up the distance table for each code. You can compute the code. You already compute the code between all this centroid. You already know all the centroid. For example, you know in this space there are 256 centroids. Okay, you can compute all the centroid distance in advance. Okay, so at this moment, when you know X is belong to which list, when X you know is quantized to this cell, to this region, and you want to compute the distance to all the other cells, you just look up table. So here is the lookup table text 0. You don't need to apply any distance computation here. You just look up table. It's very fast. But for ADC, okay, you have, because in ADC you don't compute the lookup table distance in advance. So for X, we have to use its original vector to compute with all the central one by one. Okay, so let's the computation, distance computation is here. Okay, so this is for encoding and then table lookup. But for compute all the data in your database, we have to compute their distance of both SDC and ADC. Their compressed is n by n. N is the number of your data, and the n is the number of the segment. Okay, so in SDC, because you have the data, and each data you have to check n times. Okay, so your compressed is n by n. But for ADC, similar, because ADC you will also build a distance table between the X and all the central. Okay, so after it, you just look up the table. So in this stage, both methods they just apply the table lookup to do their computation. So both are n by n. And after it, if you want to find the case noise distance, so the result, you just sort it, and the complexity will be n plus k log k log. It's not n log k. It's smaller. If we in the traditional sorting algorithm, if you want to find the case noise distance, okay, the complexity will be n log k. And traditional is n log n, right? If you sort it n values, the complexity should be n log n, right? But if you just want to find the case noise, it's n log k. But if n is much bigger than k, it can be reduced. It's a more efficient algorithm. The complexity is just n plus k log k. It's another very fast algorithm to deal with when n is much greater than k. Okay, so it's a general analysis for the time complexity compared with the SDC and the ADC. Okay, any problems? figure show you the comparison between x-symmetric and asymmetric. The x-axis shows the true distance between 2 points, and the y-axis shows the asymmetric distance between the 2 points. If they are accurate, it should be, if it's the distance should be aligned in the diagonal, right? So if the distance is 0.6 and the estimated distance also 0.6, then should be, the point will be in here, along the diagonal. But because we apply the symmetric, you see the symmetric is the red point. You see the distribution. Any 2 points, I see it's a set of 1,000 vectors. Any 2 points, you calculate the distance. Okay, so the symmetric one is the red point, and the asymmetric one is the blue point. So it's clear, you can see that blue point is more closer to the diagonal, right? And then for the red point, they are lower, much lower than the diagonal. So it means asymmetric is more accurate than the symmetric. Sorry, asymmetric is estimation for asymmetric distance is more accurate than symmetric. Okay, any problem? So you just use some data to demonstrate, to show you that the asymmetric distance is more closer to the diagonal, means it's more accurate. 所以这个就是它的对角线啊，就是说是最准的。就是你预估的跟真正的距离是一模一样，就会在对角线上面。那你可以看到那个非对称的做法，它的蓝色的一点啊，都比较靠近对角线，那红色的呢就比较远离的对角线。所以很明显就是非对称的，就是 asymmetric 的这种做法是比较好。This slide shows give analysis for distance error for the ADC. Okay, generally, so first we use this equation to show the mean square distance error. It can be written as this. So the first term is your distance between x and y, and then the second term is the x and the distance between the x and the quantized vector of y. Okay, so this is the real distance, and the second term is the estimated distance of ADC. So their difference is regarding as the mean square distance error. Okay, then it's simply an integral of all the data x and all the data y. Next, we use a triangular equality. Okay, like this. So this equality shows that the distance to the xy is here, the red line. Is smaller than the distance between the x to the q of y and the y to the q of y. So the red line is smallest. The red line is smaller than this line plus this line. So it's called a triangular equality. 好，三角不等式嘛，看得出来吧？就是红色这条线呢，它的长度一定是比它的第二个边跟第三个边的长度加起来，一定比大还小，对吧？好 ，so the length of xy must be smaller expressed like this. Okay, so we can reorder their position. We just move. We just move this turn to the left hand side, and then put a square to both sides. Okay, so we can get this equation. We'll just reorder this turn. And you can see what it is. This is the set to the NSD we define as our first equation. Right? The left hand side is the set to MSD. Okay, so we can say MSD of Q, and so actually can be represented like this. We just add the integral of Px of Py. Okay, it should be MSD smaller and or equal than this, and this is smaller than this one. And what it is? What it is? This is actually the mean square error between the original y and the quantized y. Right? Y and the quantized y. Their distance. We call it the quantization error. So here we give another term called NSE of Q, means the mean square error of the quantizer. So actually it's the distance between the original y and the quantized value of y. So it shows you the NSD has an upper bound by the mean square error of the quantizer. Okay, so here is our conclusion. So the distance error of ATC is bounded by the NSE of the quantizer. So if your quantizer is good, so your distance error of ATC is also, it will be lower than your NSE of the quantizer. So if it's smaller, it will be, if it's small, the NSE will be smaller. So you should think to make your quantizer as good as possible, so that your calculation for ATC can also get a smaller distance error. Okay. Any problem? And this page considers the memory consumption. Okay, so we consider how many memory you have to use with different methods. Okay, first is a K-means. So K-means, if you have a K centroids, and each centroid you have D dimensions. In total, it's a codebook size, right? It's a K by D is a codebook size. You need to store the codebook in your memory. And how about the assignment complexity? When you do the assignment, it means give you a query or any vector. The vector you have to compute all the centroid, and the centroid dimension is D. So you have to compute all the centroids with their distance. So the assignment complexity is also KD. Okay, so the next is another clustering algorithm called a hierarchical K-means. So what is the hierarchical K-means? Think about this, a small example. The hierarchical K-means is like this. So here we have two branches for each clustering. So first we do the two means clustering. This means that case 2. K-means clustering, and we set case 2. So it's a two means clustering. So the data is separated into two clusters. And for each cluster, we apply the k-means again to separate into two subclusters. So it's called can form a hierarchical structure. Okay, so it's called HKN, the hierarchical k-means. Okay. So how about if we apply a hierarchical k-means, HKN? What is the memory use? In their paper, they say the memory use is like this, but it's wrong. So it's so it should be here. Okay, you can see the memory used to store the code here. Actually, you have to store all the nodes, right? All the nodes you have to keep in your memory. So in total, the number of the cluster is this, and each cluster dimension is b. So it should be this term times the b. Okay, so here give a wrong analysis. So I correct in here. And how about the assignment complexity? The assignment complexity will not depend on the number of k because it's hierarchical. So you see, each time give a data x, you just see which cluster is close to you, and then suppose the left node is closer to you, then you go to here, and then compare these subclusters. Okay, so you just need to go one path. You don't need to compare all the clusters, all the central. Only go to one path to compare along with this centroid. So it's much faster. So you see, the assignment complexity is much faster. No more k. Sometimes k is very large, but here the k is replaced by BFL. BF is your branch. Here we have two branches. So BF is 2. L is your level. Here is the 2 level. So L is also 2. It's much smaller. Okay, so if you use HKN, you can get a very excellent speed up when you're doing the assignment. Okay, so the memory you still use a lot of memory to store all the central vectors. But for assignment, you can speed up a lot. Okay, any problems? For HKN. Okay, and finally, we see product quantization PQ. So for PQ, the memory use is a number. You have n segments, and each segment you have k star centroid, and each centroid you have d star dimension. Okay, the total memory use is this. You see, it's very compact compared with the k-means. K-means here is k, but here is k to the 1 to the 1 over n. Right? So it's very compact. Remember, k-means PQ is very compact to use the memory space. Okay, so it's very compact here. And for the assignment, it's also very fast. Okay, you just need to check any segment, and each segment you check k star centroid, each centroid is d star dimension. Okay, so the total complexity is also very efficient. So you can see, by using the PQ, you can get the advantage of very memory efficient, and also assignment is very fast. Any problems? Okay, so finally, I show you the complete architecture that we propose to do. Now it's become the standard. If you use the face library, they already implement. It's called the IBF ATC. Okay, that I will show you the code. Yeah, just set up use one code, one line code, and set up with your parameters. Then you will build up the IDF ABC for you. Okay, so it's a complete structure. First, the upper part is how to build up your database. So give the Y. So the upper bar, for the upper bar, we build up the database, give the database vector Y. Okay, so we first serve a course quantizer. A course quantizer, you can treat this like a first level k-means. Okay, so you apply k-means, build up the code. Okay, so the Y, so we will check which code, which central is closest to Y, and we will assign into the corresponding centroid. Okay, so you can see here is we separate your space into several clusters, and this data is closest to this centroid. So we assign this data to here, and this is inverted list, and this inverted list will keep is data ID and also is PQ code. Okay, so it's the first level clustering. We call the course quantizer. And after it use the course quantizer we can find its corresponding cluster. Okay, and then we will continue to compute its residual. The residual is computed by just use the Y, subtract from your centroid, the corresponding cluster centroid. And you will get a smaller vector, right? After the subtraction, you will get a smaller vector. And then we will use the residual, we call it a residual. We will use the residual to do the PQ. So here we apply PQ and generate this code, the PQ code here. So okay, maybe you will ask why we want to use the residual to do the PQ, not use the original vector to do the PQ. Okay, there are also some experiments to show that if we use the residual to do PQ, it's more accurate. Okay, the reason is also intuitive, because after the computer residual, you use the residual is usually very small. The value is usually very small. The vector value is usually small. And when the value is small, the quantization error will be also small. Okay, the reason is simple and intuitive. 好，就是有人试过了，用原来的向量去做 PQ， 跟用它的 residual 来做 PQ， 哪个效果比较好？residual 的 PQ 效果比较好，因为 residual 后，你算完 residual， 它通常它的值都很小，它的值就都是小小的，不像原始的向量那个值都很大，它这个 residual的 vector 值都很小，因为你值很小的时候，你做那个 quantization， 它的 error 也会变小。我们自然嘛，你的值比较小，再做 quantization， 它也不会，它的值域就会比较小，就这样子理由。Okay, so we use the residual to do PQ to get a more accurate result. Any problem? Okay, for the bottom part, here we show how to do the query. So given a query data X, okay, then we first apply the same, go to the first level quantization for the course quantizer to see, we want to find the which cluster is close to X. And then we will also compute the residual. It's just compute the residual is the X subtract from the centroid. You get the residual. Then we use the residual to compute the symmetric distance computation here with all the candidates. Okay. Then we will do the sorting to select the top k distance as our search result. Okay, any problems? The whole architecture is called IDF ADC. And then you can find this instruction, just use the face library. And with this parameter setup. Okay, so here you say okay, we will compress the vector into 128 blocks, and each block, each segment contains 16 codes, and also use the SIMD. This distance computation is also a built-in function in face library. Okay, there are more parameters you can use here. So if you are interested in using face library, okay, you can check it. You can check it by yourself. Okay, so that's all for product quantization. And its next derivation is called OPQ. OPQ means the optimized PQ. Okay, how to do the optimized? Also, this paper published in CBPR is the top of the best conference in computer vision. Okay, so and interesting. At the same year in CBPR, they also accepted another paper called Cartesian K-means. They proposed the same thing by two different groups. Okay, so at the same year. This paper is of course by Microsoft, and this is by I forget, it's by American top university. But this paper OPQ has a higher citation number, higher number of citations than this. Okay, so for OPQ, OPQ try to optimize the product quantization by using the space decomposition and also the quantization corpus. The space decomposition is involved in locating your space and also reordering your dimension. And they propose two different methods. One is the non-parametric, and the other is the parametric, under the assumption of the Gaussian distribution. Alright, so the OPQ is defined, the problem is defined as this. The motivation is to decompose the D-dimensional space into n segments, n subspace. And for each space, for each subspace, we will build a subtotal. And their idea is to use orthonormal matrix R to represent the space composition. Here, the R is usually determine the dimension reordering and location. So its optimization is expressed like this. So here you see we want to find to minimize this error. This error is R is the rotation matrix of use R, and pi with some table in your codebook. Okay, so X is we can find is indexed in this codebook, and the through this codebook we can find is reconstructed vector. So it will be reconstructed based on this codebook, and we hope the reconstructed vector and the original X should be, the error should be as small as possible. So it's the same. Right? It's formulated as the quantization error. But now it adds a rotation here. The additional parameter, rotation. Okay, so rotation, we will rotate the X, and also the real codebook will also apply the same rotation. And the rotation is to be it's called orthonormal. Okay, so the orthonormal definition of R transpose times R is equal to the identity matrix. It's called orthonormal. Okay, it should satisfy this constraint. Okay, so this definition for OpenQ. Any problem? So first we check the non-parametric solution. In non-parametric solution, there's no data distribution assumption. So we just solve it. To solve it, there are two steps. First step is we fix R and try to fix the rotation matrix, keep it fixed, and try to optimize your code. Okay, so here we just say, okay, we'll let the X head to be Rx and the C head to be Rc. Okay, and then okay, you can rewrite the above equation as this. And because this is fixed, R is fixed, okay? Rx is fixed, okay, so we just try to optimize your code. Okay, so here, you simply run the k-means. Run k-means to find the best code in step 1. Okay, then after it, in step 2, then we'll fix our code to optimize your rotation matrix. So here, your minimization term, your error term is fixed. We want to maximize your, we want to optimize R. And this equation, because R transpose R should be identity. So there is a analytic solution for it. Okay, just use this equation. If you want to solve this, such that R transpose R is identity, you can find. You want to find R, so you just do the SVD to find the USB matrix, then R will be VUT. It's an analytic solution for it. Okay, so we just use this equation to do the to do SVD, singular value decomposition, to find the root and V, and you can find R. Okay, so you find the optimized R, and then you can go back to find the optimized C, then optimize R. Repeat and repeat until it's converged. So it's called a non-parametric solution. This is the algorithm that's shown in the paper. So here you see the step 1 here. Okay, so we will repeat to do the k-means. The for iteration, the for loop is to do the k-means. The k-means just only do once. You remember the k-means we can apply it to run several times, right? Until it converges. But here, they say you don't need to run several times. You just need one iteration k-means is sufficient. I think they hope the training can be very fast. Okay, so they say the one iteration k-means is sufficient. Okay, so in this paper, they propose the second solution for the parametric solution under the Gaussian distribution assumption. So it means that each dimension of the vector is independent Gaussian distribution with zero mean. Okay, so based on this assumption, okay, so they already have a theory about it. So the distortion should be satisfied with theory. And this is the extension to the PQ version. So it's extended to this. Okay, just ignore how to derive the theory. Okay, just know there's already a theory to talk about. Under the Gaussian distribution, the distortion is satisfied like this. And because we want to apply the notation, the matrix R to the data, so the above derivation will be derived as this. We find this lower bound for your arrow, for the above arrow. So you can see actually the above arrow will be expanded by your number of segments and your covariance. Okay, so we just ignore this part because it's very complicated. Okay, so we go to the conclusion directly. So based on the parametric solution assumption, the low bound is achieved by the following two criteria. Okay, first, your dimension should be independent. So to make your dimension independent, you just apply PCA, principal component analysis. Okay, then after you apply the PCA, you know PCA is actually to rotate your space, right? To rotate your data in a high dimensional space. So after it, then we want to balance your space variance. So they based on the above theory, they already get that the product eigenvalue is a control, will influence this one. Okay, so we want to make it to be balanced like this. So the step 2 is to reorder your principal component to balance your product of the eigenvalues. So it can be expressed like this. Okay, so although it looks very complicated, but in implementation it's very easy. First you do the PCA. Do the PCA, you will get the eigenvalue and the eigenvectors. Right? Okay, then second, suppose I get the PCA and like this. 10, 5, 3, 1. This is a social order. This is the eigenvalue. And not list the corresponding vectors. Okay, but after PCA you get, for example, four eigenvalues. And we want to reorder it so that to satisfy, make the criteria to be balanced. So just choose. Okay, choose the first one is the biggest one. So we will put them into two sets. Okay, so into two segments. Okay, so there are 4 dimensions. We want to divide into 2 segments. Okay, so each segment you have to how to order it. First, 10 should be put on the first segment. Okay, and next will be 5. 5 should be not put here. It should put in the second. This is the first segment. This is the second segment. The 5 should be put in the second segment. Because we its general idea is like this. Okay, so this is what is they say here. To make the two segments to be their eigenvalue product to be as balanced as possible. Okay, any problem? Alright, so the OPQ algorithm generally rotate the data and perform a GQ and try to find the best rotation matches and the best cohort by using GQ. So, but with this, we can how somewhat to reduce the quantization loss. And the rotation plays an important role here. So rotation by using a rotation like the PCA, performing the PCA can be correlated with the data dimensions relation, and also try to balance the variance inside the graph. And the question is, which one is better, the OPQ non-parametric or parametric? Which one is better? You see, the parametric is based on the Gaussian assumption, right? And it looks like it has a solid theory about it, but in practical, non-parametric is better. Okay, in the experiment, they show that non-parametric is I think it's easy to understand, and also it performs better than parametric. Also, this is because the data distribution is not always follow the Gaussian, right? So this assumption not always works. But if you already know this data is indeed following the Gaussian distribution, then maybe OPQ with the parametric will perform better. But I think okay, they already showed that the non-parametric one is better. So here is an illustration for OPQ. And this is the original data space. You can see if we just use the original data space and to apply the PQ, you will generate some centroid like this and some combination of the centroids of the first segment and the second. There's combination. Actually, don't have any data inside the combination, right? You see, here is blank, it's empty. But after you rotate the data, I just rotate the data maybe 30 degrees. You see, just rotate the data from here to here. Just rotate it counterclockwise, rotate the data. Because here, and in the new space, you see, I only use these centroids and every centroid combination of the first segment and the second segment, they all has the data inside. You see, they all have the data inside, unlike each one. So this shows the rotation has some good properties. After the data rotation, you can usually find a better representation for this data. So it's recommend you when you want to do the clustering or want to do the quantization. Okay, so you can apply the PCA first, and then do your next step. Is usually get a better result. Okay, any problem?